Hello, good morning. Okay, let's start class. Let's look at the Stokes theorem and see what we can get. Okay, now we consider a closed surface. Okay, closed surface. Okay, so let S be a closed surface. Closed surface means surface has no boundary, just like a sphere, for example, right? So closed surface could be surface like that, sphere, could be like something like a donut, right? It's closed, no boundary, okay? Then oriented, okay? Oriented means you can always assign a normal vector everywhere. It becomes a normal vector field. Oriented everywhere there's a normal vector. Okay, it continues. So that means oriented. There is a smooth normal vector field over the sphere, over the surface. Okay, oriented means there is a smooth normal vector field, okay, over the entire sphere, entire surface. Okay. It's not guaranteed, not always. Okay, and those are the oriented. These surfaces can be oriented. Okay, you can have orientation, but there's a claim bottom which cannot be oriented. Okay, there are some surfaces I'm not going to talk about here. Right. So what we're going to do is in the space we have a vector field, right? F have a vector field in the space. So what I'm going to do is, okay, this is S. Okay, I draw a closed curve, okay, in that direction, matched with orientation, okay, for the top orientation. But for the surface is divided into two parts. Okay, dividing into two parts. So let me draw this surface here. Okay, so making it looks like easier to understand. Okay, so I draw this closed curve here, and that's a C1. Okay, this match was this vector field. This is S1. Okay, and here S2. So in order to match the orientation, I have to reverse the orientation. So C2 is also, you know, this is also the boundary of S2, but the orientation different. So C2 equals negative C1 in some sense. Okay. So then, okay, then remember the integral of the curve of the vector field, okay, can be decomposed into the integral of the sum of the two integrals. Okay, right? Then we apply the Stokes theorem. We apply the Stokes theorem to each surface with a boundary. For the first one, yeah, you can parameterize this by R, okay? For that one, this can be integral of C1, okay? Integral of the C1 and F dr, okay? So in order to match the orientation, okay, so this will be, you know, you have to reverse the order. So for the second one be R2, okay? So R1, R2, they have the same opposite orientation, okay? And plus C2 F dot dr, okay? since since they have the same opposite orientation, actually this is the same the curve is the same curve, but the orientation is different. So that should be equal to 0. Okay, they are C2 equals C negative C1. That means they have the opposite orientation. So this becomes 0. That way it cancels out. Okay. And to understand this, yeah, this is it's easy to see that. So that means for a closed surface, the curl of the vector field, the integral, the surface integral must be 0. Okay, must be 0. Okay, so this is what we want to know about closed surface. So my question is, do we have a similar theorem as the Green theorem for the closed surface? Okay, recall that, right? Recall Green theorem. Okay, the Green theorem is for the domain on the xy plane. Okay, and the vector field is going to have only 2 components, P and Q. Okay, then this integral of the vector field dr, okay, C, okay, this is going to be the integral, okay, of C f dot t ds, right? Okay, this is going to be the double integral of f. Actually, this is going to be, well, let's see, how can I describe in more details? This actually is, if you want to use this notation, this is actually the curl of the vector field was K and the dA, okay, the dot product, okay, in 3 dimensions. More details is going to be P dx plus Q dy, okay, is going to be double integral and the Qx minus Py dx, okay, this is what I want. Now I'm going to describe it in a slightly different way. Okay. Okay. So this is our formula, right? This is a Green theory. Okay, the vector field is still the same vector, phi, p, and q here. Okay. And here's a curve. So for a curve, you have a unique normal vector, okay, to the curve, right, in dimension 2. Okay, this is a t. Okay. So yes. Okay. So how do we find what is the relationship between t and n? If t is going to be a and b, n is going to be I think b negative a. Okay. Get it? Clear, right? And they're perpendicular, and the angle between them, it's easy to check. Okay. So, okay. So I'm going to look at the vector. Instead of t, I'm replaced by n. Okay, I look at this. I find out this is a P and the Q, okay? And the difference is, okay, as the difference is here is, this is the vector, you see, I get to put P, B negative A, right? ds, okay? So I can express it in the form P times B times C minus A times Q, okay, ds. But I can also express it in the form, okay, negative Q and the P, and this is yeah, let me check the orientation. Okay, yeah, negative, that's true, yeah. So, and the A and the B, right? The inner product ds. So this is going to be just dot T. Okay. So, so by the stock sum, the green sum, that is going to be the second part, px, minus the first part, y, okay, dA. Okay, so after express it, this is going to be px plus qy and dA. Okay, and this is denoted by dvi as the divergence of a vector field in dimension 2. Okay, so in other words, I have this actually much better notation. Okay, this is going to be the divergence of f and dA. Okay, that's interesting. This is an interesting formula. Okay, in dimension 2, it follows from the green theory. Okay, it follows from the green theory. Okay. Yeah. So this is so a green theory, if it's stated in this form, it's better. Actually, you can call it green theory too. Okay, and instead of tangent vector, okay, because for the tangent vector, okay, you can always think about that, right? So this is a vector, right? Here's tangent vector T, and here's AB, and this normal vector N, and B and the negative A, right? So F dot N ds is going to be actually is going to be this is a P and a Q, right? And B negative A ds, right? I don't need to put ds here. Okay, and this can be written, yeah, let me repeat again, BP minus AQ, okay? But this can be written in the form like that, plus B and P, right? So that means it's negative Q, P, and A and B. And that is going to be negative Q, P, and that's right. And there's a tangent effect. You see, so you can switch to that, and this may be what I should do. Okay, this is related to F, right? So what is the notation here? Here, if the vector field here is F is in that form, P and Q. So in other words, you twist it. Okay, so this will be F. Let's use, I'm going to use this notation, okay, perpendicular to the original one, okay? So that will be negative Q and P, okay? So this is going to be, okay? And the curve of this vector field becomes a divergence, okay? Becomes a divergence of the original vector field. The curve of this vector field times the perpendicular, right? yeah, in the three-dimensional space, it will be divergence of F. Okay. But now, so for the curve, right? In the two-dimensional plane, you can talk about tangent vector, you can talk about normal vector. But for a surface, for a closed surface, maybe I have another hole here, right? Okay, for a surface like that, okay, surface can be very arbitrary. You know, I can make a, right? So for the surface like that, it's oriented, right? And you can use the imagination to draw many kind of surface. So you can only talk about the normal vector. You cannot talk about unique tangent vector because the tangent vector at the one point form a plane. There's just so many. So you cannot talk. So only integral you can look at is this, right? Right? You cannot replace n by t. So in the dimension 2, maybe it's better to consider only the integral of the inner part vector field is a normal vector, right? Anyway, we're going to generalize the same, and it turns out to be here's the same. That is it's a closed for a closed oriented surface in R3. Okay, you can have, I can change the W integral of this. It's a wonderful formula. Okay, it is a wonderful formula. Okay, very similar to the one we just derived for dimension 2. Okay, yeah. So you can convert a surface integral vector field to triple integral. Okay. Okay. As long as this is a closed surface. If it's not closed surface, for this surface integral, you may change it to a line integral. Okay, and that is a Stokes theorem, right? Compared to the Stokes theorem, a Stokes theorem is not for the closed surface. Stokes theorem is for no, we don't have a, yeah, we cannot change the arbitrary surface integral like that. Yeah, unless f is a curl of some another vector field. Okay, so in general, you can only change the surface integral like this type to a triple integral. Okay, compare. So if you only consider this kind of surface, okay, and if it's, so this is the direction C, okay, you only consider this half of the chopper, the surface cut into one piece, and this is a C. Then in general you don't have a you can convert it. Okay. Okay, you can only convert the to the line integral C of G actually, and dr if F is the curl of some vector field. Okay, if you think about in the calculus, you know, you have the so-called fundamental theorem of calculus. So if the function is derivative of another function, then you can evaluate the values at the two end points, right? So from one dimension to 0 dimension, okay? And here's a similar, you can go lower dimension, right? And a two-dimensional integral become one-dimensional integral, okay? So this is compared to the Stokes theorem. Okay, we compare to the stock. The stock theorem, you can only work on the surface with a boundary. Okay, and if we have this integral vector field, the inner product was a normal vector field, then only when F is a curl of another vector field, you can change it to a line integral. Okay, so there are two possible ways to convert a surface integral vector field. Okay, one is to the line integral, another one to the triple integral. Either one go up or go down. Okay. So this is the very interesting theorem. Okay. So I'm going to let's discuss one example first. All right. And the first example is a simple thing. Okay. So we have a sphere. Okay. We probably find the relationship between the volume formula and the surface integral, and there's a surface area and the volume relationship with R, right? So this is in three-dimensional space, X, Y, Z. Okay. So the vector field is going to be X, Y, Z. Okay. Okay. This is a vector field. Okay. So the normal vector at the point X, Y actually is going to be normalization here. Integral of x squared plus y squared plus z squared, which is 1 over r x, y, z on the surface, on the sphere, right? So this is a normal vector. All right, so the inner product, and the inner product is just equal to 1 over r, right? 1 over r and x squared plus y squared plus z squared, and that is r squared over r, so it's r. Okay. Okay. The divergence of the vector field is going to be partial derivative of y with respect to y, partial derivative z with respect to z, which is going to be 3. Okay. So now let's look at this integral. This integral is going to be the surface integral. Here's r ds, right? So that means r is taken out. By definition, but this surface integral gives you the area of the surface, right? But on the other hand, this is going to be the triple integral of the ball, right? Yeah. And that is divergence of f dv. The divergence of f is going to be 3, right? So that means you take a 3 out, you can have the triple integral over the ball increased by the sphere. That is going to be the volume of the ball. Okay, so now it's clear we have the formula. The volume is going to be r over 3 times the area of the surface of the sphere. Okay. If you know the area of the sphere, you can get the volume of the ball. If you know the volume of the ball, you can get the area of the sphere. The relationship is such. Okay, it's great. Right, and we know that the area of the sphere, okay, 4 pi r squared. Then you get the volume of the ball. Okay, depends on which one it's easy to compute. I think the volume of the ball is much easier to compute. Use a spheric coordinate. Okay, use a spheric coordinate. Then you can get the area of the sphere. Okay, now let's take a look at yeah, let's look at another problem. So we have the vector field. It is going to be, let me draw it. Okay. F is going to be x squared, y squared, z squared. Okay. So S is the boundary of the solid, right? This solid is described as follows. Solid E, okay? So Z is between 0 and the square 1 minus y squared. And X is between 0 and 2. And I think Y, so let's try this. Let's sketch the graph, okay? It looks like that. This is a y-axis, z-axis. Okay, this is the x-axis. Okay. So z is between z. Actually, z is positive, but x squared plus y squared is z. So actually, it's going to be a semicircle. Okay. So there's no restriction. X is between 0 and 2. So you can have this semicircle. So if you connect it, okay, it looks like that. Okay, clear, right? Now x is between 0 and 2. Z is between 1 and 0 and square. So actually, y is between negative and the positive, right? Yeah, anyway, this is a solid. Now we want to evaluate this surface integral, okay, which is S normal vector and ds. So the normal vector is a point to all sides, okay? At the bottom is go down here, right? And here on the top is like that. So it's positive oriented, okay? With this orientation. So the question is, if you ask you to evaluate this surface integral over a closed surface, you should think about the divergence theorem. The reason is, otherwise, you see how many pieces here? The surface consists of 4 pieces, and you have to parameterize each side, right? Each surface. Then you have to evaluate the 4 surface integral. That took too much time. So you should quickly convert it to the triple integral E and the divergence of F and the dV, okay? Then all you have to do is consider divergence. Divergence of F is partial derivative of the first term plus partial derivative of the second term with y, partial derivative of the third term with z, with respect to z. Okay, so you get 2x plus 2y plus 2z, right? It's not too bad. All right, so this is going to be the triple integral of 2x plus y plus z and the dv. Right, now, how do we simplify, how do we evaluate this triple integral? I think to evaluate this triple integral, you can you can do, there are several ways to do, okay? Oh. Phi is gone. All right. Sorry for that. All right. So what I'm going to do is, okay, so this is a D I'm talking, okay? So this is a D in the XY plane, right? So for every point X and Y in D, okay? And we know that this is between 0 and the square 1 minus Y squared. Okay, so this triple integral can be written as double integral, okay? And that is dA, right? And here's a single integral Z, okay? So that is from 0 to 1 minus square Y squared. So X plus Y plus Z and twice of that, okay? Yeah, so we have yeah, you can, this is a line segment, right? And in space, here's X and Y. And actually, the third component, three-dimensional third component is 0. Right? And then Z, the Z value for the points on this vertical line is between 0 and the square 1 minus Y squared. The upper bound is the square root of 1 minus Y squared. Okay, so now you can evaluate this single, single integral. So the entire derivative of this single integral is X times Y Z plus half of Z squared, and evaluate at these two endpoints here. Okay. Okay. So you will get X times X plus Y, okay, and 1/2 1 minus Y squared, and the dA. So the next step is to try to evaluate the integral with respect to X is between 0 and X is between Y is between -1. It's a right now it's a rectangle, right? The domain D is a rectangle. So this is from 0 to 2, X plus Y. And that is dx and the dy, okay? So the entire derivative of the above function, there is only one term containing x. So you will get half of x squared plus yx, okay? And this will be half of x 1 minus y squared. So you just plug 2 for x, then you will get, this is 2 plus 2y, and here just 2, so it's 1 minus y squared and dy, okay? That's it. Now, so how do we do this? Next step. Okay, we have 3 integrals here. We separate, okay? So one is 4, right? The second is 4 gets y. The third one, and the negative to 1 minus y squared dy, okay? I think this is going to be 0. You don't need to waste time to do that because it's other function. Okay, on a symmetric interval, and the negative part, the positive part cancel out. You can use substitution to evaluate, but how about this part? This part is nothing but the area of the semicircle. If you want to find the area of the semicircle, you end up with this integral, right? So this will be the area of the semicircle. It's a 4 pi over 2. Okay. And plus, this is going to be 0, right? Plus antiderivative of that function is y minus 1/3 y cubed. Evaluate 2 endpoints. Okay, I will get 2 pi plus, I get, yes, 2 pi, right? So I get 4 over 3, I think. Yeah, 4 over 3. 4 over 3. Okay. So this will be the answer. I think it's much easier than you directly evaluate the surface integral. After you convert to this triple integral, and because the solid is not that complicated, so it's not you just convert it to an iterative integral and evaluate step by step. Okay. Right, our next problem, I want to consider the upper hemisphere, right? Right, and this is a surface. Actually, is, the vector field is going to be the vector field is going to be x, y, z. Okay, no problem. Okay. Okay. S consists of the hemisphere, just a hemisphere, okay? Okay. Z equals 1 minus x squared minus y squared. And the bottom part is closed, and the disk in the xy plane. X squared plus y squared less than equal 1 in the xy plane. Okay, so it's closed. Okay. And we want to evaluate the surface integral f ds, okay, which is f dot okay. So now you have a so what is the best way to solve this problem? Okay. We can try 2 different ways. Okay. So there, if you use a stock, if you use the divergence theorem, okay. If you use the divergence theorem, we will get right. You will get E is the solid enclosed by the surface, right? This with the divergence f ds, okay, dv, right? And the divergence of this function is just equal to 3. Okay. Right? The divergence of this function is 3 because it's now partial derivative of x with respect to x equal to 1, right? So this is going to be 3 of the volume of the E. We know the volume formula for the whole sphere. Half of the sphere, first of all, this is going to be 1 cube, right? Divided by 3, because only half of the sphere, so divided by 2. So answer is just 2 pi. So you don't need to do too much computation here for this problem. Okay. Right? So use the divergence theorem, you can solve the problem very quickly. Now, if you want to evaluate the surface integral directly, you have to parameterize the sphere, right? You can use spherical coordinates, okay? And then the integrate over then you get a double integral. Okay? But there's 2 surfaces here. 2 surfaces. One is a disk, other one is a semi-sphere, right? So you have to separate these 2. Separate the integral into 2 integrals. Okay. And it just becomes more complicated. So whenever you see a closed interval, okay, then a closed surface, you should work on that. Sometimes even you don't, if you're not given a closed surface, okay, you still can use this to solve the problem. Okay, I modify this problem. Okay, so f is still this same vector field, but the s is just as a up semi-sphere. Okay, was up semi-sphere with a boundary. Okay, right, and orientation is this is orientation given. Okay, so evaluate the surface integral. Okay. Now, to solve this problem, you can do it directly. Okay, no problem. Okay, how do you do that? You have to parameterize, right? So to do this, you have to parameterize. I think it's going to be right, every point, right? Spherical coordinates, right? So you have phi here, and that's a theta, right? So theta phi, right? It's going to be sine phi cosine theta, sine phi sine theta, right? And cosine phi, right? Then if you forgot, you can find out from the book. You have to compute the cross product, right? Of the partial derivative. So let me check if we already have a formula. No, I cannot memorize this formula. Okay, it's a sphere surface integral. Okay, surface integral. There's somewhere already have examples. I'm pretty sure, because the sphere is very popular. Okay. Yeah. Okay. Yeah, I think. Oh, the parameterization is slightly different. Yes. Okay. So it's already given. Okay. This is on page 1169. Okay. So which one should be? They use yeah, the parameterization. So when theta increase, you get this direction, right? R phi. And I think which one should be first? This is R of theta and R phi. If the cross product, maybe we should use a phi first theta, because then this matches with this matches was a normal vector. Okay. So phi first. Okay, let me use my right hand. Yeah, so this match was a normal vector. Okay, anyway, so you will get sine phi cosine theta, sine phi theta, sine theta, and sine phi cosine phi. Okay. Yes. All right. So then, then you have to find yeah, this integral ds becomes this double integral, right? And the inner product of dx, right? So f of this value, this is just x, x, y, z, right? So just look at the inner product, and the inner product we'll get is yeah, this just x, y, z, right? So x is the sine phi cosine theta. So sine cube phi cosine square theta, sine cube phi sine square theta, and plus sine phi cosine square phi and the dA. Okay, and then you simplify it. You will get sine cube phi, because add them together, sine cosine square theta, sine square theta equals 1. Okay. Then you take sine square phi out. No, sine phi out. Then you can get sine phi plus cosine square phi. So yeah, so it's 1. So it's just going to be integral of sine phi dA. But this is the integral from 0 to 2 pi, from 0 to pi, from 0 to 2 pi. Okay, so the first part is 2 pi. Okay, and that is going to be 2, so it's 4 pi. Okay, it's 4 pi. Yeah, you can solve this problem without any trouble. Now, what I'm trying to do is, this is an S, right? I add this part. This part is called S prime, okay? The bottom part. So, so you look at the union of these two surfaces, okay? F dot N ds, okay? And this can be, this is by the divergence theorem, right? And we already did a computation here. The divergence of, it's 2 pi. I remember this is going to be 2 pi, okay? So we already did that, you know, the integral, the triple integral, yeah, it's 2 pi, right? Yeah, it's 2 pi because divergence is going to be 3. So it's going to be 3 dV. It's a 3 of the volume of E, and that is going to be 3, 1/2 4 pi over 3. So it's 2 pi. But S prime, okay? So then this is going to be you separate them, right? You want to evaluate this. Instead of evaluate this directly, I evaluate the surface integral on the disk. This is much simpler because on the disk is a flat, okay? It's a flat. And the normal vector is pointed to that direction, it's n, right? And this is going to be negative k, okay? So the vector field, let's see, okay, this is the S over that disk, this actually is the D, the disk D. Over that disk, F is going to be X, Y, the third component is 0. And this N is actually 0, 0, negative 1. And that is going to be, yeah, that is going to be, what? dA. Okay. So that will be going to be 0 actually. Okay, that is going to be 0. Okay, I think about problem I made mistakes. Oh, correct. This is a 0. So you only have this. Okay. So therefore, the answer is it's going to be 2 pi. Now, why I got 4 pi? Here, why I got 4 pi? I think that was a small mistake here. Phi is actually is between 0 and 2 pi because it's semi-sphere, not a up semi-sphere. Okay, so that's why this is a 1. So that's why you have a 2 pi here. Okay, but the semi-sphere phi is, you see, look at this phi, right? Phi is largest possible value for phi is half pi, not a 1 pi. Okay, I just realized that. Okay, so sometimes you are given complex sphere, but if you add another piece to make a closed surface, then the other piece is simpler. Then you can convert the integral, transfer the integral over that complex sphere to an integral over simple sphere, plus the triple integral on the region enclosed by these two surfaces. Okay. All right, let's take a look at another example in the book. And this is, there are many problems here. Okay. We are going to use a divergence theorem to calculate surface integral. Okay. So we are asked to use a divergence theorem. Okay, the first part of the exercise is to verify the divergence theorem for the vector field. Okay, and to verify means you have to evaluate the separator. One is a double triple integral, other one is a surface integral, and to see if they match. Because somebody says this is true, you don't understand the proof, that's okay. But you look at the examples. If the examples always show that both are equal, then you should trust this is correct. And yeah, right? Okay. Right, so let's take a look at problem, I can do problem number 8. I can also do problem number 10 and 12. Let's do the problem number 8, okay? That's quiz 8, and that's problem 8. So the vector field is going to be at every point it's going to be here as x cubed plus y cubed I, y cubed plus z cubed j, z cubed plus x cubed k. Okay. And S is a sphere with radius 2. And the center at the origin. Okay. The orientation is always usually, the normal vector is point all side, okay? Evaluate, otherwise they're different by sign, okay? Evaluate this, okay? Surface integral. So this is a sphere. Okay, how do you do that? Okay, this is a plus. Yeah, you can express this surface integral as a different way because at the point x, y, z, this is belong to the sphere S2, right? Then the normal vector at x, y, z is going to be 1/2 of x, y, z. Okay, because the length of that vector is going to be 2, because the radius is going to be 2, right? So that's why I divide by 2. So this surface integral, now the reason I want to re-express it because it's sometimes possible to get to the answer quickly. You don't need to apply the divergence theorem, right? So this is a surface integral, the product of those two, right? It's 1/2 x times the first component, so x cubed plus y cubed x, and 1/2 y cubed plus z cubed y, 1/2 x z cubed plus x cubed and z and ds. But this is a very complicated function. We are not able to evaluate it quickly. Right? We are not able to evaluate it quickly. Right? And you have to use, I'm not sure, it takes too much time to evaluate. So you should try divergence theorem. The divergence theorem will be the divergence of f and dv. Then this will be much easier to evaluate. Okay, that's a partial derivative of x cubed plus y cubed, partial derivative of y cubed plus z cubed, partial derivative of z cubed plus x cubed and dv. Okay, so let's simplify a little bit. Okay, there'll be 3x squared, 3y squared, 3z squared, and dv. Okay, I think that this is a simple integral. Okay, and it's a triple integral of the ball. So we should use the substitution rho. This is going to be sine phi cosine theta, y equals rho sine phi sine theta, and z is going to be rho cosine phi. Okay, phi is between 0 and pi. Theta is between 0 and 2 pi. Rho is between 0 and 2. All right. And then what do you remember the Jacobi, right? This is this is denoted by the region. So it's changed to the triple integral of that region. Okay. And x squared plus y squared plus z squared is going to be rho squared. And the dv should be changed to, dv prime over this rectangular box, right? So this is what I remember, this is a square and sine phi and dv prime. Okay, dv prime is d phi, d theta, d rho. Okay, this is a triple integral over, the triple integral, and we did it before, right? Yeah. Yeah, you can go back to, let's see, this formula, rho square sine phi, that's correct, okay? So, when you take a quiz, it's open book, you can double check the formula, okay? Yeah, so then because it's the region I is a rectangular box, right? So it doesn't matter which one is first. And the rho is, you can say rho is from 0 to 2, and then from 0 to pi, right? And then from 0 to 2 pi, right? And 3 rho to the 4th power, and d theta. Yeah, 0 to 2 pi, and d phi, and d rho. Okay. Okay. So step by step, we evaluate this integral. It's 2 pi, so it's a 6 pi right now. Right. Then the integral of sine phi is going to be 2 over the interval from 0 to pi. So it's going to be 12 pi. Okay. And then the antiderivative of this will be 1/5 rho to the 5th from 0 to 2. Right. And finally, you get 12 pi 2 to the 5th by 5. Okay. You can simplify a little bit, but this is that's it. That's all we can do. Okay. Yeah. So as long as it's a closed surface, you should always try to use a divergence theorem to evaluate the surface integral right there. Okay. So because the divergence is easy to compute, just partial derivative of the first component with respect to x plus partial derivative of the second component with respect to y. Okay, and then third one. Okay, that's not a I will try to explain the problem number 12, but maybe I don't have a time to finish the computation. Okay, so we have a vector field x, y, z at every point, and that is going to be xy plus 2xz, right? And x squared plus y squared j, xy minus z squared k. Okay, so S is the surface of the solid, okay, bounded by cylinder x squared plus y squared equals 4 and the two planes, okay, z equals y minus 2 and z equals 0. Okay, so you have to sketch the graph first. This is the cylinder, right? X-axis, Y-axis, Z-axis. Z equals 0 is this. Now Z equals Y minus 2. Now be careful about 0 equals minus 2, okay? When Y equals 0, Z is going to be negative, somewhere here, okay? Just look at the line in the YZ plane. When Y equals 2, Z equals 0. Okay, so this is going to be like a strict line, right? So the plane actually is going to be like this. I cut to the surface, I cut to the solid in this form. So actually, this is my solid. Can you see, right? Okay, this is my solid. Okay. So the surface is closed surface, but consists of 3 pieces. Okay, so you can, if you want to evaluate, this integral, I think it's better to use a divergence theorem. Okay, so use the divergence theorem, you can get triple integral. Okay, and then the divergence of f dv. So let's calculate the divergence of f. The divergence of f is partial derivative of this function with respect to x, the partial derivative of this function with respect to y, and partial derivative of this function with respect to z. Okay, so let me quickly compute this. Okay, the first part is just y plus 2z, and that's 2y, and here minus 2z, right? Minus 2z, double check, okay? So y plus 2z, 2y minus 2z, yeah, no mistakes. 2z canceled out, I only get 3y. This is triple integral. Okay, only get 3y. Okay, so now, the triple integral should be converted to iterative integral. Iterative integral, how do we do that? This is my D, the disk. Okay, the disk is D, right? Yeah, it's going to be x squared plus y squared equals 2 squared. So D is going to be x squared plus y squared less than 2 squared. Okay. So for each point x, y in D, z is between 0 and y minus 2. Okay? Yeah, z is between 0 and y minus 2. So this becomes a double integral dA over xy, and then here's the integral for z. Z is between y minus 2 and 0. Here's y and here's dz. Okay? Right? So it's going to be the double integral here, and y is a constant with respect to z, so just y times the difference of these two functions. So 0 minus y minus 2. Okay, after simplified, I get 2 minus y is 2y minus y squared, 2 minus y, and dA. Okay, So this is the integral over. This is the integral over the disk right now, right? So for the disk, it's better to use polar coordinates, okay? So x is going to be r cosine theta, y equals r sine theta. R is between 0 and 2, theta is between 0 and 2 pi, okay? And so that is going to be, and that is my d prime, right? Yeah, so that's a double integral. I'm not in big hurry to change the iterating. 2y, 2r sine theta, right? Minus r square sine square theta. Okay. And what is dA? Okay. What is dA? And dA is just r, okay? So dA prime, polar coordinates. Okay. So this is going to be the integral from 0 to 2, and from 0 to 2 pi. And I have a 2r square sine theta minus r cubed sine square theta and d theta and dr. The integral of the first one must be 0. Why? Because the integral of sine theta over the integral from 0 to 2 pi must be 0. So you only needed to calculate, yeah, the second part. It's -3. And okay. So to evaluate this inside one, I didn't need to find the antiderivative because sine square theta is going to be 1 minus cosine 2 theta divided by 2, right? So the antiderivative of that function will be half of theta minus a quarter of sine 4 theta, okay? Evaluate the two endpoints. And only the first term is not going to be 0. Okay. So 2 pi over 2 is just pi. All right. Then you find the antiderivative of r cubed. It's a quarter r to the 4th power. Okay. So my answer is and 2 to the 4th power over 4. So that's just the -4 pi. And that's it. So yeah, we have to, yeah, in many problems here, as long as the surface is closed, convert it to the triple integral, okay? Then evaluate the triple integral, okay? This not necessary to be sphere, could be like this, like a portion of the cylinder, okay? And then you should know how to convert the triple integral to an iterative integral, okay?